IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Sammy said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Brian Risch of the Prysmian Group from North Carolina, USA, who will be presenting his paper on enhanced solvent resistance and flammability requirements for harsh environment and industrial optical fiber cables. Brian Risch is a Materials Technology Manager for Prysmian Telecom North America. He holds a BA degree in physics from Carleton College and a PhD in Material Science and Engineering from Virginia Polytechnic Institute and State University. Brian has more than 20 years of experience in the study of structure, property relationships, and polymeric materials and materials reliability, with 14 years in the fiber optic cable business. Prior to working for Prysmian, Brian worked for Alcatel and Draka, specializing in cable materials and fundamental material reliability. Brian also worked at Hewlett-Packard, performing research in electronic materials, reliability, and failure analysis. Brian, we welcome you to present at today's IWCS webinar series event.
Thanks for your introduction. First of all, I think if anybody would like a copy of the slides, probably the best way, if I'm to send the papers or the slides, just contact me by email, and that would be a good way that I could just send them out directly to anybody. We're going to talk a little bit about some enhanced solvent resistance and flammability requirements for harsh environment and industrial cables. We'll go over some standards and different industry requirements, things like that. This presentation was originally put together for the 2015 IWCS Symposium in Atlanta. I've added a couple slides that I thought would also be interesting that are related to industrial environments, especially for explosive environments, which is another interesting area. We're going to start off with just some introductory material. Then we're going to talk about some of the various requirements, mostly in terms of U.S. standards, but I will briefly hit on some of the European standards because they're different and some of the intent is different. We'll go over some of the experimental methods used to evaluate solvent resistance and flammability of cables. Then I'll go through just some representative results of some different products and materials that can be tested and relative performances. Certainly this would not be all-inclusive, but it's representative. It shows, the kind of inherent variability that you can see in the materials. Then we will conclude, and there'll be some time for questions. If I'm not able to address your question today, you can feel free to contact me. My contact information is listed on the cover slide and should be available from the webinar. So, first of all, where would be an application for industrial and harsh environment cables? Some of the markets here, especially in North America, a lot of these areas would, kind of be in the Gulf region where we have some of our refineries and chemical plants, as well as up in Canada and the Dakotas now. Basically, mining, petroleum exploration, extraction, and transport, refineries, other chemical plants, other industrial plants, and then along the pipelines, we're seeing a lot more pipeline monitoring, infrastructure monitoring for both safety and spill detection, things like that. There's a lot of good reasons to upgrade to optical fiber cables where applicable. There's some factors increasing the demand. Due to the price of oil now, the oil exploration now is basically stopped. The extraction is not economical for a lot of the North American assets such as the oil sands up in Canada, but this is kind of a temporary trend, and this will, grow again in the either the near or not so near future. There's also a lot of our industrial infrastructure is rather old. The average life of oil refineries in this country is 30 years or older. So there's some new constructions and a lot of upgrades for safety, efficiency, things like that. And then, replacement of old systems, control and instrumentation with newer systems for better safety, reliability, efficiency, and then just convergence of industrial automation. So there's a number of advantages to optical fiber cable. I guess first of all, the cost of optical fibers has been going down, and the cost of copper has been going up. So that's, economics is a good advantage. A big advantage I'm going to talk about a little further is that the optical fibers are non-conductive. So basically no grounding is required with dielectric cables, and there's no chance of sparking or resistive heating or shorting in the cable. That's a big advantage for industrial and especially explosive environments. Optical fiber cables, they have electromagnetic immunity, so you wouldn't get any crosstalk or interference with motors or anything like that in any control signals. That's also a very good advantage. You can get a smaller size cable with optical fibers, a higher data transmission density, large bandwidth, and then, with increasing concerns over security, it's very hard to hack into an optical fiber network. So there's a lot of advantages. One advantage that I did want to add a little more information, and this is new information, is basically deployment of optical fibers in explosive environments. And there's a number of different types and classes of explosive environments. So basically it's defined by the type of hazard that's present and basically the nature and severity of the hazard. So basically, probably the most common hazard would be a class 1, which you'd have flammable vapors or gases, and that might be around an oil refinery, even a gas station, around the gas pumps. If you think about how potentially dangerous that is, you fill up your car with gas every day, and you have all this electronics and motors and pumps and wires there. Those all have to be rated products. Combustible dust can be a big hazard for locations such as sugar refineries, grain silos, things like that. The dust particles can be explosive, and even a small spark can set those off, and there's been several large industrial accidents. And then there's also, other types of fibers or flyings could be a hazard. So there's a number of hazards, and typically any type of cable, whether it's optical fiber or electric cables, you imagine you have, if you have a processing plant, you may have conveyors or pumps that also require motors, so it's very important to keep good safety there. There's different divisions in terms of the level, like a Division 1 where the materials are normally contained would be like a gas station or something like that, where everything is normally, or that would be a Division 2, where it would be normally contained and it would be exposed only in a spill or something like that. And Division 1 would be, a more severe requirement. For the electric cables, it's pretty complicated in terms of the deployment and actually the regulations, which I'm not going to go into depth. That would be a complete talk on its own. Talk about the risk of hazard with the cable, even the temperature rating of the cable, and the volatility and the vapor pressure of the fluid that you're dealing with. So it can be very complicated for electrical cables. And then, there's always the risk. There's grounding, and in some cases the cables might have to be put in a hermetically sealed conduit, so it can be, rather complicated. And the electric cables must always be specially listed for use in explosive environments. The big advantage over optical fiber cables, of course, is the optical fiber systems are, using optical energy to transmit the light. So, lower energy, no chance of sparking, and the temperature rise with an optical fiber cable is negligible. So really, there's not a chance of creating a sparking event, with the optical fiber cables. And there's a number of regulations, but basically, if we take a quote from the OSHA specifications, basically, if the heating is not more than 100 degrees, and the equipment really doesn't need to be marked, so optical fiber cables would fall under this classification. The care must be taken, though, when deploying an optical fiber cable into an explosive or through an explosive environment, that the proper sealing from the entrance and the exit of the cable is done to prevent leaking of vapors outside of the environment. And this would also be applicable for any electrical cables. Of course, if the if fiber optic cable has any type of electrical conductor, it falls under the normal restrictions for electrical cables. And then additionally, if there's any type of metallic or conductive armor on the fiber optic cable, that armor must be grounded. And then there also can be local restrictions above and beyond what I may have discussed. Some of the additional requirements for harsh environments for optical fiber cables are, would be applicable to normal deployments. For mining cables or something like that, there might be additional enhanced compressive resistance, impact, or bending or temperature requirements. If the cables are mounted vertically, they could come under heavy loads due to the long weights and deep shaft depths. Typically, industrial cables are flame resistant. Even if they're deployed outside along pipelines, we always recommend getting a flame resistant cable just to prevent the cable from acting as a fuse. So even if it's not a requirement for building codes, that is always a recommendation. A lot of these cables in industrial plants go between inside and outside of buildings, so they have to be both suitable for indoor and outdoor resistance, which means that they're going to have UV resistance. As I mentioned before, the lifetime of these plants is very long, so you want to have a long lifetime for the cables. And then, in many of these industrial environments, solvent resistance is going to be required. And depending on the environment, there can be a number of different solvents. So really, for optical fiber cables, there aren't they're not explicitly called out in a lot of these standards. There are some standards on solvent resistance, but even in terms of the types of solvents covered by existing standards, it is somewhat limited, and I'll go into that a little bit. So we'll talk about just a couple representative cable designs and different fiber counts with different materials of construction, and just look at how these different cable designs do in some of the industry standard burn tests and solvent resistant tests. And basically we're looking at a couple dual jacket cable designs, and basically we're looking at changing the inner and outer jacket materials. And basically we're looking at the two main cable designs we're looking at are an LSCH cable, that has an LSCH inner and outer jacket. And then we have an industrial cable with a chlorinated polyethylene outer jacket and a PVC inner jacket. We'll take a little bit to go over the hierarchy of burn testing, which is kind of interesting, and this can become rather complicated when you pull in all the international and European specifications. The European specifications are in flux now due to new CPR regulations. Those are construction product regulations in Europe, which are trying to harmonize and enhance the flame test requirements. So basically, a lot of these older European flame test requirements are becoming outdated. They're being replaced by stricter tests, but the individual countries have the leeway to establish the performance in the test. So it's very complicated and evolving. I'm going to kind of steer clear of that quagmire and focus mostly on the U.S. tests. The severity of the test starts off with basically Bunsen burner tests, and I've shown the VW1 test that many people should be familiar with, and the European equivalent, which is a very similar type of test with the same type of flame source, different test requirements, different flame propagation requirements typically for the European tests. There's a number of 20 kilowatt ribbon burner tests. This would be applicable for what is known as an FT4 test or a UL 1685 test, IEEE 1202 test. These tests are essentially nearly identical. They vary mainly just in the flame propagation limits between these variants on the test. So really you can perform one of these tests and get a rating for all three depending on how extensive the flame propagation is. The 50339 test is a multiple cable test, 20 kilowatt. That would be one of these new CPR type tests, and then the UL 1666 test is commonly referred to as a riser burn test. It's a full-scale, three-story, larger energy cable test to kind of simulate a riser in a real-life situation, a very common test here in the U.S. And then the NFPA 262, often referred to as the plenum or Steiner tunnel test, is the most severe test, and that's a horizontal test. And there's really no European equivalent to that very difficult requirement. So we've defined the experimental parameters for the tests, and then we have different performance criteria. You can see for the CPR, CPD test, there's various levels of performance criteria that you can see for most of the U.S. standard tests. As I mentioned before, there's a difference between the FT4 and the UL 1685 in terms of allowed flame propagation, although the test is virtually the same. VW1 is just a single cable test. And then the UL 1666, it's a much larger scale test. The UL 1666 has an additional requirement, which is the maximum temperature. The heat release is measured in the plenum cable test. And then many of these tests have the option of getting a low smoke listing, which is different than a low smoke zero halogen listing, as I'll discuss a little bit in the future slides. Here's just an example of one of these 20 kilowatt ribbon burner cable tests. The basic configuration I'm showing here with the ribbon and the ladder is common to all of these tests, but each of these tests has a different arrangement of the cables depending on cable size that's also specified for the test. We're going to move on and talk about different oil and gasoline resistance ratings. This idea it's kind of old news for people in the electric cable business, but there's really not any commonly specified requirements for oil and gas resistance for fiber optic cables, although they're commonly deployed in the same places that electric cables are, maybe alongside of electric cable that would be required to be rated. So, the recommendations that we have is that really the fiber optic cable should be subject to the same type of testing and requirements as electric cables. Although a failure of the jacket on a fiber optic cable might not create a spark that creates a catastrophic fire, it can still make a critical system go down, such as a monitoring system or a fire detection system or something like that, or security. So it's equally as important. There's different levels. The oil resistance one is basically there's a specified test oil that's used. There's just different exposures. The oil resistance one is a 96-hour test that requires 50% of retention. Oil resistance 2 is a longer-term test, requires a higher elongation retention. if you pass the oil resistance 1 and oil resistance 2, you can basically do a gasoline resistance, which is looking at a mixture of basically a kind of a slurry of water and toluene to kind of simulate a gasoline mixture or spill. And there are, again, higher tensile strength and elongation requirements for this test. And this, again, is a longer-term test. So basically, as you move down here, you get a more and more severe test. But you see those tests are really limited to a rather narrow range of materials. So although there are these industry requirements, you may want to test your industrial cables to a wider range of solvents, especially if you're dealing with polar solvents. So we'll go on and talk about some of the results here, and these are just typical results. So we have, we've looked at 72 and 144 fiber count loose tube cables, and we call these industrial cables. The one class is the low smoke zero halogen. We call it heavy duty because it's got a dual enhanced jacket for enhanced crush resistance. And I'm not going to talk about those requirements because that was another topic. We also have this CPE oil and gas cable, 72 and 288. So this is a chlorinated polyethylene outer jacket, which is a great compound, very good mechanical properties, good low temperature impact, and very good solvent resistance. Not all LSCH compounds are created alike. Not all CPE compounds are created alike. But these are kind of representative, good compounds that we had. We made these cables and we tested them to the 1685 IEEE 1202 burn tests, and you see the requirements of 150 centimeters of propagation. All of the cables easily passed. The smoke release rate was also very good, and then the total smoke generation was actually good for both, cables. So this is it's a CPE. Of course, with chlorine in it, it does have halogen, but you can see it will pass the low smoke requirements. The low smoke zero halogen did have a lower total smoke release, but both of these are the low smoke rated. But because there's chlorine in the CPE jacket, it's not a low smoke zero halogen. So that's the distinction between low smoke and low smoke zero halogen. The LSCH cable, we decided we want to get a riser UL 1666 rating on this cable, so we tested to this full-scale 3-story riser test, and we had very good results, over a 50% margin, 5 feet of flame propagation, really good. Temperature well below the temperature limit, so these cables performed very well. We did not test the CPE cable for this type of application because the environments we normally deploy this do not require it. But, my guess is that cable would probably perform very well. To just kind of look at, relative performance without going into great test details and, looking at how different jacket materials might stand up in these type of designs. So if we put a standard polyethylene jacket on the cable design, well, it is halogen free, but the cable is you basically have candle wax on the outside of it, so it's not really going to be able to have any flame rating. Polyethylene has relatively decent solvent resistance, though, but generally we try to stay away from this with, around any kind of flammable environments. The CPE, it can get the low smoke rating, easily pass the IEEE 1202 type testing, but again, as I mentioned, there's chlorine, so it's not halogen free. During a fire, there can be some release of corrosive gases, so there are some applications where you might not want any damage to equipment or things like that. So in those cases, an LSCH compound may be preferred. Typically, you're going to have some sacrifice on solvent resistance there, but the LSCH compounds can get very good riser cables made with both low smoke and halogen free. To improve your solvent resistance with LSCH, You can get cross-linked LSCH compounds. Typically, you do need to sacrifice to get a good cross-link performance, to sacrifice some of the flammability requirements of the material. PVC compounds, there's a wide range of PVC compounds. Generally, the PVC compounds will not do as well as CPE in solvent resistance, but they can get a very good rise or burn rating and low smoke. They're not halogen free, and I do mention an oil resistant PVC because those are sold. PVDF has really good flame rating, a very low smoke material, but of course it's got fluorine in it, so it's not halogen free. For solvent resistance, here's kind of a dramatic example with a really nasty fluid. It's a hydraulic fluid, which is more aggressive than oils and things like that, and just kind of a comparison between what it might happen with LSCH and the wrong fluid compared to a more properly selected jacket material. So we don't want to have product failures or have jackets coming off, and field failures like this have occurred with improper material selection and cable deployment. If we look at the CPE solvent resistance results for the oil and gas resistance, you can see, under all the tests, very good retention. The CPE easily passes all the test requirements, even after the gasoline aging. So, that's the CPE is a very good choice for solvent resistance. I am going to say this with a word of caution, though. There's a wide range of compounds which are called CPE compounds on the market. Some of them are actually blends of PVC and CPE that have, very compromised solvent resistance. Some of them may not meet the same requirements. So, internal screening is always very important in any material selection. And to start off to these industry standards is a good start. For special deployments, such as for aeronautical cables or something, additional testing with hydraulic fluids, maybe with polar solvents and de-icers, may also be desired, although there aren't industry standards for those types of fluids. Looking at the LSCH, kind of your standard, industry standard LSCH compounds, typically will not do well for oil and gas resistance. They're better than many PVC compounds for short-term and room temperature exposures, but for longer continuous exposures, really most LSCH compounds are not suitable. You can modify LSCH compounds most easily by cross-linking them to make them able to pass an oil and gas resistance test. And I gave a talk about a cable for Europe because the CPE compounds are not as much in favor in Europe. So this is more of an approach that's used in Europe with the cross-link jackets to get the oil resistance. PVC compounds can be very poor, and this is a representative PVC compounds. Not all PVC compounds will perform this poorly, and they're with proper formulation of PVC, you may be able to get a PVC that has that'll pass the oil and gas resistance. But typically, across a wide range of solvents, the PVCs will not do as well as a CPE outer jacket. The PVDF outer jacket really is almost impervious to most hydrocarbon type solvents. So it's very good. It's used, in a lot of aircraft type cables and stuff. But on polar solvents, some hydraulic fluids and things like that, PVDF can be more prone. So again, you need to take a look at the specific environment that the cable will be deployed and consider the jacket material. Okay, so coming to the end of the talk here. So when we're looking at industrial cables, there's multiple risk factors. There's really a wide range of cable deployments. So you have to look at the complete environment, including the type of solvents, what type of stresses the cable is going to be seeing, what are the thermal excursions, is it exposed to UV, what is the required flame rating, and then, what is the, other reasonable requirements. So for optical cables, you can kind of get a pass on some requirements. Do you want to take that pass, or do you want to really meet what the other electric cable requirements would be for that application? The outer jacket material, as I've shown, is really a very limiting factor and controlling factor in your performance of these cables for a number of these performance criteria. And I've talked about the fire resistance and the solvent resistance in particular today. And the cable design does play a role in this as well. And just in conclusion, one of the recommendations that I'd like as a takeaway for this is that, where you have chemical exposure for your cables, you should really look at not just what's the requirement for fiber optic cables, because there's really not a specific oil and gas requirement, but you really want to look at, they should be rated to the equivalent requirements that the electric cables are rated to. All righty, so I am ready to conclude if you want to take over the questions.
Yeah, Brian, first of all, thank you very much for the presentation, and there are some questions. I'll start out with the first one here, which is, are solvent-resistant and flammability requirements for cables in harsh environments fairly consistent around the world? Do different regions require different material solutions?
Yeah, there's definitely, in terms of the fire resistance requirements, they are very different, and they're actually different by industry even around the world. And I focus mainly on the U.S. resistance. Now, the solvent resistance requirements, there is a European equivalent kind of to the oil resistance ones, but neither the flame test requirements nor the solvent resistant requirements are harmonized throughout the world, and also it's unlikely that they're the same between electrical cables and fiber optic cables. Now with the CPR regulations in Europe, the intent is to bring some of the requirements for electrical and fiber optic cables for fire resistance together. But again, there's still from country to country the requirements or the performance in the test. So the test is standardized, but the performance levels will not be standardized from country to country. So I guess the short answer is definitely no. There's a lot of work to be done there.
Okay. Next question. Why have optical fiber resistance and flammability standards lagged behind the equivalent copper cable standards, and when will they be the same?
Yeah, that's a very interesting question. I think they have lagged behind because, the introduction of optical fibers has been newer, and especially the introduction, fibers to the network, fiber to the premise came a little later than, the deployment of optical fibers in long-haul applications. So, I'm seeing each year new applications for optical fibers, and, it takes a while for the standardization bodies to update the standards. Right now you see a lot of the, in the industrial cable standards, there's mentions of fiber optic cables, but it can be as simple as saying that, fiber optic cables may be deployed in trays, for example, and that, they may specify a flammability requirement, just for safety, but nothing about explicitly defining performance requirements. So there's definitely some work, and that's going to have to go on in the standardization bodies. But I imagine that'll take years, But I think we are the people to kind of start it within the industry. If we start making our cables to the same specifications, that's certainly a start. And then consider the practical application and the risk.
Okay. Next, while fiber optic cable systems eliminate the risk of sparking and an explosive hazard scenario, are there other issues related to solvents in industrial environments that uniquely cause performance or transmission issues in optical fiber cables?
Yeah, that's kind of getting into another area. There's a number of different things that can happen. Normally, the jackets on an optical fiber cable are kind of designed to keep the solvents from getting to the fibers. Solvents can cause a number of coating issues with the fibers. So if the optical fibers become directly exposed to an aggressive solvent, it can cause issues with the coatings, which could cause attenuation issues. certain chemical species can directly interact with the glass itself and create absorptive centers. One example is the impact of radiation. In nuclear power plants, the fibers have to be specially designed to resist radiation. Hydrogen, for example, can have, depending on the fiber design, can have a very large impact. So some environments, especially for oil exploration, for fibers being deployed in high-pressure environments, special fibers and special mitigation, well above and beyond what I'm discussing needs to be employed for those very special applications.
Okay. Next, even though the NEC higher level fire safety requirements, such as riser or plenum, cover internal networks, have you seen any industrial environments that require this higher level fire resistance for cables to minimize risk?
Yeah, there's different levels. So even the plenum burn test is not necessarily the highest. So there's another level which I didn't discuss in this test, which is basically there's a kind of a resistance to fire type test, or basically cables that can actually survive and transmit data during a fire. So there's some U.S. as well as European test specifications for crucial fire alarm systems and things like that, which actually require functionality of the systems during a fire and survivability. And oftentimes these type of applications require ceramifiable jacket materials that kind of will hold together and protect the fibers. So there's, beyond what I'm talking about, there are these other applications. These are pretty low volume markets, though, compared to what I'm talking about, which are the more common industrial markets where the, most of the systems don't need to keep operating during a fire. And in a lot of the systems that you might want to keep operating, they might be electrical systems, such as being able to shut off a valve or something like that. But there are higher level standards.
Okay. I'm looking at about 3 more at this point. We've got enough time. Based on your experiments, other than oil, gasoline, and hydraulic fluid chemicals, do CPE compounds tend to fare better than CPE blends in which other chemicals?
Yeah, in terms of, there's a number of, like the blends basically with any other chemical is not going to do as well as the CPE. So, we've looked at things like acetone and, MEK, things like that. So generally the blends do not work as well. But this is a very general statement because there's so many CPE compounds and blends out there. But, basically, what I'd recommend when evaluating the materials, do not take, the vendor's word at face value, and you need to do benchmarking across, a representative number of chemicals to cover the deployed environment. And, to start off with the industry standard recommendations is a very good start. If you don't pass that, I wouldn't even recommend moving further with a material. If you pass those, that's probably good for most applications, but there may be specific applications where you want to expand your product testing.
Okay. Next, since there are no standards for chemicals other than oil and gas, do you test the solvent resistance at room temperature or at specific elevated temperatures? And how long are the exposure times?
Yeah, we have a variety of chemicals that we test, and, oftentimes we will test them at room temperature and some elevated temperatures. In some cases, with materials that have a high vapor pressure, we do not bring them up to a very high temperature for testing just due to safety risks in the lab. So there's, just a wide range of materials and temperatures that we test. It could include de-icing materials. So de-icing materials, typically you don't need to really worry about a high temperature exposure with those. So some of it's common sense, some of it's looking at the actual properties and, the risk in your lab with the materials, and some are looking at the environment. Now, with something like the hydraulic fluid, we would test that at an elevated temperature and lower temperature, and that's like the military hydraulic fluid, the low viscosity hydraulic fluids are about the harshest fluids that I've seen for a lot of these compounds. They can really tear into some of them, especially at high temperature.
Okay. An added value proposition for LSCH compounds is the halogen-free aspect. Where do you feel LSCH can improve the most to offer more flexibility in wire and cable? Oil resistance, price, or processability?
Boy, that's a trick question. It really depends on the application, So a lot of the LSCH products, especially in Europe, are more of a commodity product that are deployed in even the flame retardancy requirements for a lot of these cables in Europe are not as harsh. So, in Europe, there's a wider range of LSCH compounds available. They're generally less expensive, but, maybe the flame performance on many of these European compounds wouldn't be, as good. So that's one area, price can improve, but, you look at what's happened in the market in Europe already, there's been the response there. I'd say oil resistance is probably, I know there's some new compounds being worked on, and the oil resistance is something that probably can be improved the most. The cross-linking can help things out, but kind of the combination of the oil resistance and ultimate properties, would probably be good. A lot of times when you're tweaking something, though, you can turn the knob on processability. So I have looked at some materials that have, been difficult to process, and and I don't think there's one right answer to this question. And in terms of, okay, do you want? Are you in the market for the biggest volume? Well, then you probably want the best in terms of cost and ultimate properties. But in terms of to get the the best for a specific target market, I'd say work on the oil resistance and ultimate properties. But I don't think there's one right answer. There's a, you're not going to have one LSCH compound in your toolbox that's going to be the right tool, for every problem. So, you really need a variety of LSCH compounds if you're going to have, a truly diverse product portfolio.
Okay, great. That concludes the Q&A segment. I was able to cover all the questions we had submitted. Thank you very much, Brian, for presenting this today. Please note the contact points being shown now on your screen should you wish to contact Brian after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, March 18th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so they can join in and register as well. For over 60 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual conference will take place on Sunday, October 2nd through Wednesday, October 5th, 2016 in Providence, Rhode Island, USA. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.